This is the third lecture of CAM 810S. The topics: machine tool frames, coolant systems, cutting fluids, and data management. The required features for machine tool frames are mechanical stability, static rigidity, dynamic stiffness, thermic stability, and ability to absorb and damp vibrations and oscillations. An economic aspect are moderate costs. Gray cast iron is one of the materials often used. In gray cast iron, the carbon is embedded in the form of flakes. Its main properties are a good compression strength with a low tensile strength, good machinability, and moderate ability to dampen vibrations. The costs are moderate. Malleable cast iron. In malleable cast iron, the carbon is embedded in the form of nodules, which are obtained in a thermic process of the casting. Its main properties are a good compression strength, improved tensile strength compared to gray cast iron, good machinability, improved ability to dampen vibrations. It's of course a bit more expensive than gray cast iron. Another material used is mehanite, named after its inventor, American Mr. Meehan, in the 20s of the last century. During the production process, calcium silicide inoculation is done, and this reduces the size of the carbon flakes, thus improving the mechanical properties. The properties of this mehanite material are similar to those of malleable cast iron. Mineral compounds are composed of 80% of epoxy resin, and the rest is quartz gravel, sand, and stone dust. It has excellent damping properties, a good thermic stability, and a good resistiveness against chemical influences, that is, coolants. This is an example of a mineral compound machine tool frame. Because the casting of the compound is done at room temperature, wiring may be embedded in the casting. The precisely machined bed is fixed to the frame. Some machine tool frames, mainly for specially designed machines, are welded. Welded frames have a good mechanical stability and a good static rigidity, a good dynamic stiffness, but a bad thermic stability and bad damping properties. Before we continue with coolant systems and cutting fluids, I'd like to make some observations about the cutting process. Cutting processes generate heat. The friction between the rake surface of the cutting tool and the chip which slides over it, and the consequent deformation of the material generate a large amount of heat. As this impressive picture, taken with a high-speed camera at the Technical University of Münster in Germany, shows. In most cutting processes, friction and heat must be reduced, and this is done with cutting fluids. Cutting fluids have several functions: cooling, to reduce the heat; lubricating, to reduce the friction; chip removal; cleaning of work and tool; prevention of corrosion of workpiece and machine; and in grinding, dust binding. Let's look at the effects now, first regarding cooling. Tool and work are cooled, thus reducing wear and protecting edge of the cutting tool. It also improves the surface quality of the machine part. Lubrication reduces friction, increases the tool life, and reduces built-up edges. An unwelcome effect of the cutting process in which tiny amounts of material stick to the rake surface of the cutting tool in gradual layers. Lubrication also improves the surface quality of the machine part. Cutting fluids can roughly be divided into two categories: water-soluble cutting fluids and cutting oils. Water-soluble cutting fluids again can be divided into two subcategories: synthetic substances and oily substances. This diagram shows the effects of the different cutting fluids regarding cooling properties vertically and lubricating properties horizontally. There are two types of coolant systems. In flood cooling, large amounts of cooling fluid is flushed towards cutting tool and workpiece. In MQL, short for minimum quantity lubrication, an extremely small amount of fluid is supplied directly to the edge of the cutting tool. This is a typical flood coolant system. The coolant fluid is in a coolant reservoir or tank. A pump delivers the coolant to a pipe system to the working area of the machine. Pressure may or may not be controlled. That means pressure can be increased or decreased. In case of a bypass, the pump works continuously and the coolant is switched on and off by a solenoid valve. From the working area of the machine, the coolant flows back to the tank. This is a coolant tank equipped with a pump to the right and a rough filter on the left, where the coolant flows back to the tank. The pipe system is composed of a polyethylene hose and a modular flexible hose. Modular flexible cooling hoses are composed of ball joint elements which can easily be assembled and disassembled to form all kinds of shapes with different shaped nozzles. An efficient method of providing coolant directly to the cutting process is to use tools with internal coolant conduits. The cutting off tool and a drill, twist drill. Such tools are, of course, relatively expensive. This example from a cutting tool manufacturer compares grooving with internal coolant to the left and internal coolant to the right. Tool wear with internal coolant is significantly reduced. And tool life may be 200 to 300% longer. Tools with internal coolant are of course more expensive, and the machine must also be equipped accordingly. Cutting fluids may pose various hazards. Among them are health problems for persons. Cutting fluids may irritate the skin and provide skin disease. Cutting fluids mists may cause respiratory problems. When not managed properly, cutting fluids may cause environmental problems such as pollution of the environment and consequently of the water. It is therefore absolutely essential that cutting coolants and lubricants are carefully surveyed and serviced and disposed of professionally. Coolant filtering is indicated when large quantities of coolants are used. A good method to prevent the previously mentioned hazards is minimum quantity lubrication, short MQL. Extremely small quantities of fluid are supplied to the cutting edge. The advantages: a longer tool life, a dry workpiece and dry chips. It is made of biological components. There are no costs for maintenance and disposal. Small quantities smaller than 20 milliliter per hour are used. The environment is clean. There are no health hazards for workers. But it is not always possible or suitable to use this type of system. The next topic is data management. In the early days of NC technology, programming and data management was a difficult and labored affair for a few specialists. In the 1960s, punched tape technology, which earlier was developed for teleprinters and computer programming, was introduced in NC technology. Long strips of paper on which data was stored in the form of punched holes allowed offline programming. Machines were equipped with so-called program reading units, which fed the NC program block per block to the random access memory. Programming was still difficult and labored, and long tapes were required. NC programs could not be modified. This tape represents data of 1 kilobyte. In the late 70s, as hard disks and random access memories became more extensive, NC technology was replaced by CNC technology, and programs could also be stored on magnetic tapes. Today, data management has become an easy and efficient affair. Controllers are equipped with powerful hard disks and random access memories, short RAM. Programs stored on the controller hard disk can be loaded, visualized, and if necessary, be modified directly on the machine, and newly edited programs can be stored. Programs produced by an external programming software or a CAD system can be transmitted to the controller, and programs of the controller can be loaded back to the external computer or notebook. The same process applies to servers. When written documentation is required, printers are used. Programs can also be stored on memory sticks and on compact discs. But in the latter case, of course, data transmission is only possible from the disk to the controller. On concept turn 250 TCM, the panel to the right is for data input and data handling. The monitor displays the data. The panel for machine functions is situated below the monitor. You will learn more about data management on EMCO concept machines during practice. This is the end of the third CNC lectures. Please do your exercises now. An observation, the next lecture will be CNC 5. CNC 4 tools will be part of CNC 5 and CNC 6. Thank you for your attention.